In this demo, we're going to show how big data and real-time analytics can be used in the context of the oil and gas industry. We've taken a real-life scenario from an LNG processing plant where the current safety systems were unable to detect a fault. So let's get started. First, we'll log on with our single sign-on username and password. And we're given an initial dashboard designed to just give some brief information to an operator or engineer. So at the top left, we have a map of the plant showing a couple of general issues and documents related to those issues. These are also shown in more detail down here. We've also got some alerts coming out of our system. So these range from green low-level alerts, yellow warning level alerts, to red high-level alerts. We'll come to those in a second. At the top right, we have some documents. So for our dehydration process, we have some piping and instrumentation diagrams, and also some process flow diagrams, which we'll use throughout the demo. In the middle is a high-level overview, or sort of high-level structure of the plant. So for our processing plant, we have 3 trains, each with essentially equivalent processes running inside them. So let's have a look at our first train. So the processes start at the top and move down to storage and loading, and the utilities processes are used throughout the other processes. The one we're going to be looking at today is dehydration, which is the process of reducing the water content in the natural gas to a suitable level. And the reason for this is in our liquefaction process, where the natural gas is essentially cooled down and converted to LNG. If there was high water content in it, it could freeze up and block some of the pipes. So this is the purpose of our dehydration. So let's go in and see how the process is doing right now. So we're given a PFD and some gauges and graphs showing the current state of the process. I should also mention just briefly that this process is happening quite fast compared to what it would be happening in real life. So about 1 second in the process is equivalent to about 1 hour in real life. Just keep that in mind. So I'll just explain a little bit about what's going on here. The gas would come in at the top, go through a number of pre-cooling stages before being passed through these sieve beds. Typically, we have a number of sieve beds which are online and one which is offline. And as the gas passes through, water is absorbed with these beds. And in doing so, the beds themselves saturate. So these gauges here show the saturation level of the beds. And you can see the ones which are online are slowly increasing. Now, after the gas has been passed through, it will go through an after filter and then go to the next process in the plant. At this point, we measure the water content of the gas, and this is essentially our metric for determining if the process is working properly. If it is working properly, we should expect to see a water content of less than, or water concentration of less than 100 parts per million, which we can see is happening at the moment. This graph also showing this. Now, when one of the beds saturates, another bed will take its place, and the bed which is saturated will turn off and then go through a regeneration process where it is desaturated. In this process, hot gas will be passed through the bed and evaporate some of the water in the bed, or all of it. The water and the gas will then be passed through a cooler and then be separated and recycled to other parts of the plant. So this process it continually happens. Now, one of the things I should also mention is the gas that is being used in the regeneration process. It's heated using a fired heater, we can see down here. And we're also given a temperature and flow rate for this gas. So let's go into our fired heater and have a look at what it's doing at the moment. So when regeneration occurs, as we can see it is happening now, we have our regeneration gas coming in through the left, being heated up inside the fired heater and then going into one of the sieve beds to desaturate it. This is called a temperature flow cascade control loop, because what's happening is the fuel gas, which is coming in through the right here, is turning on and off depending on whether the temperature is too high or too low. So when our regeneration gas is flowing and our temperature is above the set point, our fuel gas will turn off. When the regeneration gas is flowing and the temperature is below the set point, the fuel gas will come on, essentially creating a controlled fire inside the fired heater. We also have our safety system, our safety instrumented system, as well as our interlock system. And what this is doing is monitoring the alarms for the flow rate and also the temperature. So, for example, if there's no regeneration gas flow rate, but the temperature is high, this will cause the fuel gas to turn off. Oh, this will cause the SIS to turn the fuel gas off and also the ignition off. So what we're going to do now, if we go back into our dehydration process, is we're going to create a fault somewhere in our process. Now we'll find out what exactly occurred at the end, but first we'll create the fault and see how our system reacts to it. As you can see at the moment, there are no current alerts for our dehydration process. So clicking this button, our fault has now occurred. And we've also slowed down time at this point to try and see in more detail what's happening when our system's generating these alerts. So this is why some of the graphs have flattened out a little bit. But from a high-level sort of view of the process, we can see that things are relatively normal. So our water concentration is still below the 100 ppm limit, and our temperature is slowly going up, and our sieve beds look relatively normal as well. So, but it's unusual that our system is generating some alerts. Now what they're saying is basically, it's not saying exactly where the fault has occurred, but it's saying that something's unusual, something's not quite right. So it doesn't quite conform to what we'd normally expect to see in normal operations. So just waiting for a few more alerts to be generated by our system, we can see that the temperature is reaching the set point. Our flow rate is quite high for regeneration gas. Everything else looks relatively normal. So what's being said here is high temperature gradient, so that's this graph here, and long fuel gas uptime. We'll come to exactly some more details into why these alerts were generated in a second. So now we can see that 4 warning level alerts were generated for this process. And when that happens, we can assume that there is a fault somewhere or something's not quite right. And so it generates a high level alert, which we can see has been happened here. So let's go in, clicking into this, and we'll be given a dashboard which gives us justification for why these warnings were generated by our system. We'll start on the left up here. So high temperature gradient. What this is saying is the regeneration gas temperature's gradient, or the temperature is increasing at a higher rate than normal. So from all our past data, we can see that the average temperature gradient is 153 degrees Celsius per hour with a standard deviation of 14. But we actually measured 180, which puts it in the 97th percentile. So that's why that alert was generated. Next, we have a rule-based alert. What this one's saying is, if the temperature is at the set point of the regeneration gas, we would expect to see desaturation in one of our beds. But since none of the beds have reduced its saturation level, this is an odd state for it to be in. So that's why this alert has been generated. Number 3 is another rule-based alert. So this one is saying if our temperature is at the set point, we would expect to see our fuel gas turn on relatively soon. So because the fuel gas has not turned off in the last 20 minutes, yet the temperature is still at the set point, we would consider this quite odd. And the last one, this one's a little bit different. So this one's saying from all our past data, the fuel gas, the amount of time which the fuel gas remains on, has an average of 1.1 hours, a standard deviation of 0.3, but we've measured 1.5, which is another sort of anomaly. So this puts it in the 90th percentile, which is also quite odd. So all of these individually might not be significant, but because they all happen together, this implies that there is something seriously wrong with our process. In the middle, we have two documents, two diagrams, which are related to these issues, and also the risks of so what could occur from any of these particular issues. So for example, a high temperature gradient in the regeneration gas could lead to tube rupture and essentially an explosion inside the fired heater. So that is why that one's quite a high risk alert. Now, what actually happened in real life in this process? So when this fault occurred, it actually occurred in our fired heater, which we can see here. So this is the PID showing the fired heater, and this flow switch, which we can see here, was when one of the filters was being installed inside it. It was installed incorrectly, allowing dirt to build up inside the flow switch. So basically what happened then was the flow switch was registering incorrect flow. It was registering flow when there actually wasn't any. Now what this meant was the fuel gas remained on because we saw regeneration gases being on, and our temperature we wanted to be at the set point. Our SIS and interlock system didn't notice anything which wasn't normal, because it would see a high temperature being relatively, or it would be expected, seeing as the regeneration gas was on, but there actually wasn't any. So because fuel gas was on, but there was no regeneration gas, the temperature skyrocketed inside the fired heater, and our SIS just wasn't able to react quickly enough to this problem. So in the space of about a few hours, these tubes inside here ruptured, the temperatures inside the fired heater reached uncontrollable levels, and the top half of this fired heater fractured, flying into the air and landing in another part of the plant. So this was considered a relatively minor issue because there were no injuries or anything associated, but you can see it had the potential to be quite a dangerous thing. And basically the current safety equipment didn't meet the requirement of being able to detect this sort of fault. Essentially, bad data in equals bad data out. Because it was given wrong flow rates, it wasn't able to detect a fault. And the reason why our system would help in this sort of problem and other problems is because it detects anomalies, or uses past data or our big data to detect when the current state of the process doesn't conform to normal operations. And we also want the operators and engineers to be empowered with the right information being presented at the right time, so that they can have justification for the decisions they make on the plant. So we also want them to be able to back up their reasoning, or be able to show confidently their reasoning behind making certain decisions. Thank you.